Last class we have discussed about the energy profile diagram of SN1 reaction, and in this class we are discussing about the stereochemistry of SN1 reaction. Stereochemistry of SN1 reaction. The stereochemistry of SN2 reaction was very simple because in the case of SN2 reaction only backside attack was possible, and what will happen because of the backside attack of the nucleophile, there is an inversion of configuration, and that is known as Walden inversion. So SN2 reaction is always associated with the inversion of configuration because in the case of SN2 reaction only backside attack is possible. Now let us see the stereochemistry of SN1 reaction. Okay, in the case of SN1 reaction, the first step is the formation of carbo-cation. Okay, look at here. CH3, H, and the nucleophile is coming, and the first step is the formation of CH3 plus. This is the formation of carbo-cation. This is the first step and the slow step. Okay. Now you can see that. Let us go through the. Let us discuss the structure of the carbo-cation, tertiary carbo-cation. Okay, that means carbon is having a positive charge, and you can see that this carbo-cation is having a planar structure. This carbo-cation is having a planar structure, and you can see that because of the sp2 hybridized carbon in the carbo-cation. Why? How it is sp2 hybridized carbon? You can see that carbon 6, 1s2, 2s2. 2p6, 2p2, okay, and here you can see that C plus means only C5, only 5 electrons, and you can see that 1s2, 2s2, 2p1, or 1s2 is here, 1s2, okay, then 2s2, okay, I can write it here, look at it here. Okay, look at it here, carbon in the normal state, that means ground state, 1s2, 2s2, 2p2. Okay, since there is one electron is removed, okay, with a positive charge, you can see that one electron is removed, so you get 1s2, 2s2, 2p1 because one electron is removed, that's why it is getting a positive charge. Okay, and you can see that 1s2 is like this, 1s2, okay, and 2s2, 2p1, okay, only 1. Okay, you can see that in the next step one of the 2s electron will be shifted. Okay, you can see that this is now only 1, and here it is okay, here it is this electron, and this electron is shifted to here, and this is a vacant p orbital, Now what is happening? 1s and 2p, this will mix together, and you are getting 3 sp2 hybridized orbitals. You are getting 3 sp2 hybridized orbitals, okay, and this one is unhybridized p orbital. Once again, you look at here, this is a carbo-cation, and carbon is having a positive charge, so one electron is less. You can see that 1s2, 2s2, 2p, one electron is here, and one electron, 2s2, 2p, only one electron. One of the 2s electron will be shifted. After that, there is a vacant p orbital, let it be there. Now this s electron and 2p electron, this will mix together, and you are getting 3 hybridized orbitals. These three are sp2 hybridized orbital, and there is unhybridized p orbital. Now I can draw the structure of this carbo-cation based on this explanation. Okay, this is how you draw the carbo-cation. C There are 3 hybridized orbitals. With these 3 hybridized orbitals, see CH3. sp2 hybridized orbitals are 3. Then it will form CH3. Correct? Now there is what is that? Unhybridized p orbital, vacant p orbital. Unhybridized vacant p orbital. This is the structure of carbocation, and once again I am explaining. The structure, carbocation is having a planar structure, and the positively charged carbon is having sp2 hybridized state, and you can see that there is a vacant p orbital. Now think about, you can see that this side can be taken as the front side. That means the side to which the leaving group is attached. Usually what is coming here? So that means here it is X. That means this is front side, and you can take it as this side can be taken as a back side. Okay. So why I am explaining all these things. Okay. Next step, we are explaining on the basis of front side and back side. That is important. So the side to which the leaving group is attached, the side to which the halide group is attached, that is taken as the front side, and the other side, opposite side, is taken as a back side. Okay. So this is the structure of carbocation. Carbocation is in sp2 hybridized state. It has a planar structure, and this side is taken as front side, and opposite side is taken as back side. Okay. Now let us take an example. What is the stereochemistry of SN1 reaction? Because we can explain the stereochemistry. Before that, you must know the structure of carbocation. The geometry of carbocation. Okay, you must know this. Now look at here. We can take an optically active compound, which is undergoing SN1 reaction. Optically active compound which is undergoing SN1 reaction. Example is C6H13 HCH3, and here it is Br. Okay, that means 1, 2, 6 plus 6, 7, 8 carbons are there, and in the 1, 2 second carbon there is a bromine group. So what is the name of the compound? 2-bromo. What is that? 2-bromo. 8 carbon alkane is 2-bromo octane. Okay. Actually, this is you can say minus 2-bromo octane. And this carbon is optically active. This compound is optically active because 4 groups are different groups. Definitely this compound is optically active, and definitely this compound will undergo, suppose it is on reaction with a nucleophile OH minus. Okay, what you will get? Okay, what are the possibilities of by the attack of a nucleophile on this 2-bromo octane? Okay, look at here. So keep it in mind. I am taking an example is 2-bromo octane. That this compound is optically active. This compound is undergoing SN1 reaction. That means a stronger nucleophile OH minus is attacking on this compound. OH minus is attacking on this compound. And now, what is the mechanism of this reaction? Okay, or what is the stereochemistry of this reaction? Okay, I can write it here. Okay, the first step, you can see that the first step you can see that the formation of carbocation. First step is the formation of carbocation. So what is the formation of carbocation? So look at here, C6H13. Here it is H, and here it is CH3. Okay, here it is CH3, and what is here? Here it is our positive charge, and what is plus what is formed? Br minus. This is the first step, formation of a carbocation, because the CX bond is cleaved and you are getting a carbocation. And now second step, what is the second step? This is the first step, and the first step is the formation of carbocation. And in the second step, once the carbocation is formed, the nucleophile will come and attack at the positively charged carbon. Now our nucleophile OH minus is coming, and this is important. You can see that since it has a planar structure, that is very important, since the carbocation is having a planar structure, the nucleophile can attack from the backside. This is backside attack. It can attack from the backside, or it can attack from the, and it can attack from the front side. This is front side. Correct? There are two possibilities because the carbocation is having a planar structure. Therefore, the nucleophile can come and attack from the backside. Correct? Similarly, the nucleophile come and attack from the front side. That means when it attack from the, if the nucleophile is attacking from the backside, what you will get? Backside means what will happen? OH. And you can see that if there is a backside attack, what will happen? There will be inversion of configuration. If the nucleophile is attacking from the backside, there will be, that backside attack is associated with the inversion of configuration, and what you will get? If it is backside attack, you are getting C6H13, C6H13 inversion of configuration, H, and here it is CH3. That means this is inversion product. Inversion product. Okay. That means what is this compound? Octane 2-ol. Okay. See octane. So in the second carbon there is this is octane 2-ol or 2-octanol, octane 2-ol. And since this is inversion product, this is minus, means if it is inversion product, what is this one? Plus octane 2-ol. Okay, keep it in mind, octane 2-ol. Okay, leave that this name and all will come later. Anyway, once again I am explaining. In the case of SN1 reaction, the first step is the formation of carbocation, and the carbocation is having a planar structure. The nucleophile can attack from the backside as well as from the front side. Suppose if it is attacking from the backside, what will happen? Backside attack will always result in the inversion of configuration. So that means there is inversion of configuration, you are getting inversion product. So you can name it as a inversion product. Okay, what is the compound name? Octane 2-ol. And since this is inversion to, okay, this is plus octane 2-ol, and plus, what is that? If the OH minus, if the nucleophile is attacking from the front side, what will happen? That means you are getting the same structure like your substrate. That means the place of the leaving group, what is coming? The nucleophile is coming. So you are getting C6H13, here it is H, and here it is CH3, and in the place of Br, what you are getting? OH. This is known as this is inversion product. There is no change in the configuration, and this is what is called a retention product. Retention product. That means the geometry is retained. Same structure, same geometry is retained. This is retention product. So what is the name? This is a retention product, means the same only, minus what is that? Octane 2-ol, minus 2-octane, minus octane 2-ol. Okay, and that means in the case of SN1 reaction, if you are taking optically active compound, we are getting equimolar mixture of inversion product and retention product. That means SN1 reaction is associated with racemization. We are getting racemic mixture. We are getting 50% plus and 50% minus, and you are getting racemic mixture, and that means SN1 reaction is associated with racemization, because in the case of SN1 reaction, the backside attack and the front side attack is equally possible, and we are getting equimolar mixture of positive and negative isomer. That means SN1 reaction is associated with racemization. We are getting racemic mixture. And in the case of SN2 reaction, we are always getting what is that? Inversion product. That means SN2 reaction is associated with inversion of configuration. SN1 reaction is associated with racemization. SN1 reaction is associated with racemization. That means here we are getting racemic mixture. Racemic mixture. 3n. This is because of the planar geometry of the carbo-cation. Planar geometry of the carbo-cation. I think it is very clear to you. Stereochemistry of SN1 reaction. SN1 reaction is associated with racemization because we are getting racemic mixture due to the planar structure of carbo-cation. Both backside and the front side attack is equally possible. Now another important point here we have to discuss is you can see that in the stereochemistry, another important point is ion pair effect. Ion pair effect. Ion pair effect. Just now we have discussed that in the case of SN1 reaction, we get equimolar mixture of inversion product and retention product. Inversion product and retention product. But it is seen that in many cases, inversion product predominates over the retention product. In many cases, inversion product is more than the retention product, or you can say inversion product predominates over the retention product. What is the reason? Why inversion product is little bit much higher than that of the retention product? That is, we can explain that on the basis of ion pair effect. Ion pair effect. What do you mean by ion pair effect? Again, I am coming back to the same example. C6H13 CH3 Br. This one is minus 2 bromo octane, minus 2 bromo octane. Okay, minus 2 bromo octane. Our nucleophile OH minus is coming. Okay, now you can see that what is the first step? The formation of a carbo-cation. Look at it very carefully. You can see that C6H13, here it is H, and here it is CH3. And what is happening here? It is changing to, first step is the formation of carbo-cation C plus, and what is there? Br minus. But here you can see that for a period of time, after the breaking of the CX bond, you can see that the carbon is positively charged and halide is negatively charged. That means after the formation of this carbo-cation, for a period of time, there will be an interaction between positively charged carbon and the leaving group or the bromide ion. That means there is a force of attraction. Between what is that? The positively charged carbon and the Br minus for a shorter period of time. This interaction, this is what is called ion pair effect. Because of this ion pair effect, this is what is called ion pair. This is called ion pair. What do you mean by ion pair? Ion pair is the interaction between the positively charged carbon and Br minus. Okay, this is what is called ion pair effect. Ion pair effect. See, once again I am explaining. After the formation of the carbo-cation, what will happen? This is our departing ion. Br minus is the departing ion. But there will be an interaction between the departing ion, moving ion, and the positively charged carbon. Therefore, what will happen? Because this departing ion, since there is a interaction between these two, this departing ion will prevent the nucleophile from the attack. So, what will happen? Because of the ion pair effect, the front side attack is difficult for a shorter period of time. The nucleophile cannot come and attack the positively charged carbon What is the reason? Because of ion pair effect. So what will happen? During the life of ion pair effect, as long as the ion pair effect is existing, only backside attack is possible. Now here what is that? Here the nucleophile OH minus can gamma attack. That means backside attack is possible. Attack is possible, but front side attack is shielded by, is prevented by the departing leaving group. The front side attack of the nucleophile is shielded by the leaving Br minus ion. This is what is called ion pair effect. So as long as ion pair effect is existing, as long as the life of ion pair is existing, what will happen? Only backside attack is possible. That means ion pair effect, because of ion pair effect, only backside attack is possible. And you get, if backside attack is possible means what you will get? You will get C6H13, and what is that? Here it is inversion of configuration H, and here it is CH3. That means here is what product? Inversion product. What is that? Inversion product. So as long as ion pair effect is existing, only inversion product we are getting. That means only backside attack is possible. And what is that? Here it is backside attack of the nucleophile, and you are getting inversion product. Now you can see that now what will happen after a shorter period of time, this ion pair dissociation. What do you mean by ion pair dissociation? The Br minus, this is completely dissociated and it is moved away. Okay, so you are getting, so you see C6H13, and here it is H, and here it is CH3. There is carbo-cation. Plus, here we are putting plus what is that? Br minus. Here there is no plus because there is an interaction between these two. So there is no plus here, and that means not completely separated. And after a shorter period of time, what will happen? This is completely separated and you are getting carbo-cation. Here only you are getting the free carbo-cation. Now you can see that once free carbo-cation is formed, as we have discussed earlier, backside attack is possible. Here it is backside attack is possible. As well as what is also possible? Front side attack is also possible. Front side attack is also possible. When it is backside attack, what you will get? During backside attack, what you are getting? OH, C6H13, here it is H, and here it is CH3. That means again you are getting inversion product, and okay, by front side attack, what you are getting? You are getting C6H13, here it is H, here it is CH3, and of course here it is OH. That means retention product. Okay, now you can see that there is a possibility of inversion product here also. During the ion pair mechanism is existing, you are getting inversion product. After ion pair dissociation, again you are getting inversion product. This is the reason why inversion product predominates over retention product. This mechanism is known as ion pair effect. Because of ion pair effect, you can see that during the first step, formation of carbo-cation, there will be a force of attraction. There is an interaction between the positively charged carbon and the leaving halide ion. Okay, for a shorter period of time. That time, the nucleophile cannot come and attack from the front side. Only backside attack is possible. That time you are getting inversion product. After ion pair dissociation, these ions are separated. You get completely free carbo-cation. In that carbo-cation, backside attack as well as front side attack is possible. By backside attack you are getting inversion product, and front side attack is you are getting retention product. This is the reason why inversion product slightly exceeds over the retention product in SN1 reaction. This is what is called ion pair effect, very important in the case of SN1 reaction. Okay, I think it is very clear to you. Continue next class. Thank you.